Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be looking at Chapter 8.2, Solving Initial Value Problems with Laplace Transforms. In Chapter 8.2, we now look at how the Laplace transform can be used to solve linear differential equations. This can be visualized with the bypass strategy. We can transform a dE given in the t domain using the Laplace transform to an algebraic equation in the s domain. We can then solve the equation in the s domain and then transform the solution back to the t domain using the inverse Laplace transform to give the solution to the differential equation. Consider a second-order linear differential equation. We can apply the Laplace transform using the properties of linearity to obtain the following. So given our general non-homogeneous second-order linear differential equation, apply the Laplace transform to both sides of our equation, use the linearity properties to rewrite the left-hand side. Here, we will now need to find representations for L of y prime and L of y double prime, so that the left side of the dE can be written in terms of just the Laplace of y. This will allow us to write the algebraic equation L of y is equal to some function of s. And then the inverse Laplace transform can return the solution to the differential equation. Let's first look at the Laplace of y prime using the limit definition of the Laplace transform. So here the Laplace of y prime is going to be the indefinite integral from 0 to infinity of e to the negative st times y prime of t. Of course, we'll rewrite this using limit notation. Now to evaluate this integral, we will use the integration by parts method. Now recall, for the integration by parts method, you want to pick a u portion of your integrand and a dv portion of your integrand. You'll then find your du by taking your derivative and find your v, the antiderivative. So here I'm going to let u equal the e to the negative s of t, and the dv be the y prime of t dt. For our du, we'll take our derivative. The derivative of e to the negative st is e to the negative st times, by the chain rule, negative s. And the antiderivative of y prime of t dt is just y of t. Now recall, the integration by parts method says you're going to go u times v minus the integral of v du. Thus, our integral can be rewritten as the limit as b goes to infinity of e to the negative st y of t, and this will be evaluated on the interval from 0 to b, minus the integral from 0 to b of v du, which would be negative s e to the negative st times y of t dt. And I just noticed I didn't write our dt here. Now let's see if we can rewrite this a little bit. Let's do two things. Let's distribute our limit to both terms in our antiderivative. And let's also use the fundamental theorem of calculus to evaluate this first portion of our antiderivative. So let's write this as the limit as b goes to infinity. Now remember, we're evaluating at the upper limit first, so we'll have e to the negative sb times y of b, minus, when you evaluate at your lower limit, it'd be e to the 0 times y of 0, plus, where I've chosen to combine our two negatives here, the limit as b goes to infinity of s times the integral from 0 to b of e to the negative st y of t dt. Now, for our limit, notice as we take the limit as b goes to infinity, e to the negative sb goes to 0. And y of b is going to be some constant. So since this goes to 0, this entire term goes to 0. And of course, since e to the 0 is 1, our first limit produces just negative y of 0. Plus s times the integral from 0 to infinity. Here I'm choosing to rewrite our improper integral back to having an upper limit of infinity of e to the negative st y of t dt. Recognize that here, this improper integral, by definition, is the Laplace of y of t. So this gives us negative y of 0 plus s times the Laplace of y of t. And this is the Laplace of y prime. However, our author will rewrite this as s times the Laplace of y minus y evaluated as 0. And this is our representation for the Laplace of y prime in terms of the Laplace of y. Now let's look at the Laplace of y double prime. Here we use the conclusion of the Laplace of y prime and substitution to obtain the following. Now when you look at our previous attempt, what this says is the Laplace of the derivative of some function is s times its antiderivative minus its antiderivative at 0. So applying that to the Laplace of y double prime, we can write this as s times the Laplace of its antiderivative minus the antiderivative evaluated at 0. Now let's rewrite the Laplace of y double prime using our result above. This can be s times, now the Laplace of y prime is s Laplace of y minus y of 0 minus y prime of 0. So here we're just replacing the Laplace of y prime with its definition from our previous calculation. Now simplifying this by distributing that factor of s, we can write this as s squared times the Laplace of y minus s times y of 0 minus y prime of 0. And this is our definition for the Laplace of y double prime that we will use. Now, let's look at an example where we can apply this and the bypass strategy to solve a differential equation. Consider the initial value problem y double prime minus 2y prime minus 3y equals 0 with some initial conditions. We can apply the Laplace transform to both sides of our differential equation. Using the fact that the Laplace transform is a linear transformation that preserves vector addition and scalar multiplication, we can rewrite the left-hand side as the Laplace of y double prime minus 2 times the Laplace of y prime minus 3 times the Laplace of y equals the Laplace of 0. But remember, the Laplace is a linear transformation that sends the 0 function to the 0 function. So the Laplace of 0 is just 0. Where we can use our definitions on our previous page to find representations for the Laplace of y prime and the Laplace of y double prime in terms of just the Laplace of y. So here, the Laplace of y double prime, our formula we developed is s squared Laplace of y minus s times y of 0 minus y prime of 0. Now y of 0 and y prime of 0, these are our initial conditions that are given in our initial value problem. So substituting these values gives us s squared Laplace of y minus s times y of 0. But y of 0 is 2, so minus 2s minus y prime of 0, which is negative 10, so plus 10. Similarly, the Laplace of y prime. Our definition was s times the Laplace of y minus y of 0. But again, y of 0, this was given as part of our initial conditions. So making this substitution, we have s Laplace of y minus 2. Now, let's replace Laplace of y double prime and the Laplace of y prime into the left side of our differential equation. So the Laplace of y double prime was going to be s squared Laplace of y minus 2s plus 10 minus 2 times the Laplace of y prime, which is s Laplace of y minus 2 minus 3 times the Laplace of y, and this all has to equal 0. Now in our bypass strategy, we're at step 2. We have an algebraic equation in the S domain. Now what we would like to do is to isolate all of the terms involving the Laplace of y on the left side of our equation. Anything that does not have the Laplace of y, this minus 2s, this 10, and this minus 2, don't forget we'll have to distribute our coefficient, we'll all put on the right side of our equation. So terms that involve the Laplace of y will be s squared Laplace of y. Again, don't forget to distribute R2. So minus 2s Laplace of y minus 3 Laplace of y. Now the negative 2s will move to the right hand side to become positive 2s. The negative or the positive 10, and when you distribute, this positive 4 makes 14, and we'll subtract that and put it on the right hand side as minus 14. Now the terms on the left side all have a common factor of Laplace of y. So let's factor that out and write it as s squared minus 2s minus 3 times the Laplace of y equals 2s minus 14. And now we'll divide to get Laplace of y by itself. Laplace of y has to be 2s minus 14 divided by s squared minus 2s minus 3. Now we're at step 3 in our bypass strategy. This is the solution to our algebraic equation in the S domain. Now to find our solution in the T domain, we will apply the inverse Laplace transform to find that y of t is the inverse Laplace transform of 2s minus 14 over s squared minus 2s minus 3. Now this inverse Laplace transform we have should look familiar to your work in chapter 8.1. We want to find the inverse Laplace transform of this function in the S domain. And here you'll notice that the right hand side is factorable, or the denominator. So let's work on just our fraction for a moment, using partial fraction decomposition. So notice here, our numerator would stay the same. This would still be 2s minus 14. But notice the denominator can be factored as s plus 1 times s minus 3. And with partial fractions, our goal would be to write this as a over our first linear factor plus b over our second linear factor. Now multiplying both sides of our equation by our lowest common denominator, which was s plus 1, s minus 3, we get 2s minus 14 has to equal a times s minus 3 plus b times s plus 1. Now let's make some choices for s that will simplify our equation. If we let s equal 3, by letting s equal 3, we are eliminating this first term. Now, if s is equal to 3, then the left side of our equation would be 2 times 3 is 6. 6 minus 4, 14 is negative 8. If s is equal to 3, this term goes away. If s is equal to 3, then the right-hand side becomes 4b, which tells us that b has to be negative 2. Similarly, if we let s equal negative 1, by letting s equal negative 1, we're making this factor go away. Now if s is negative 1, on the left-hand side, 2 times negative 1 is negative 2, minus 14 is negative 16, equals. If s is negative 1, then we get negative 4a. And again, this term turns into 0. And so that a has to be positive 4. This allows us to rewrite our inverse Laplace transform as y of t is the inverse Laplace of a, so 4 over s plus 1 minus 2 over s minus 3. And since the Laplace transform and the inverse Laplace transform are linear transformations that preserve vector addition and scalar multiplication, we can write this as 4 times the inverse Laplace of 1 over s plus 1 minus 2 times the inverse Laplace of 1 over s minus 3. Now, recall from chapter 8.1, or our table of Laplace transforms, what the inverse Laplace of 1 over s plus 1 is. So here you want to remember that this is e to the negative t minus 2, and the inverse Laplace of 1 over s minus 3 is e to the 3t. This is the solution to our differential equation in the t domain obtained using the Laplace transforms. Okay, I hope this is helpful. I have several more examples I want to try with you, but I'm going to do those in another resource video, so this does not get too long. So I'll see you in a moment, and I hope this is helpful.